today to introduce Professor Michael Trosset, who's the chair and professor in the Department of Statistics here. And one of my favorite things about this job of introducing speakers is that I get to look at people's trajectories, and it's really interesting to see the different trajectories. So Michael did his bachelor's work at Rice University in math, and then got a PhD at Berkeley in statistics, and then taught at the University of Arizona for several years, and then went to college at William and Mary, and since I think 2006 has been here. So I'm really thankful that you've agreed to give a talk, and really looking forward to it. Thanks a lot.
Well, thank you for inviting me, David. I arrived here in 2006, coincident with the creation of the statistics department. I think actually I'll begin by going back to when I was at the University of Arizona. I wanted to say a little bit, mainly for the benefit of the students, about sort of how I get involved in various research projects and how I think about research. And in some ways I got into this area because back in the 1980s I was given the opportunity to teach a topics course in multivariate data analysis. And like we all do, I just sort of thought, well, what do I want to learn more about? And classification and regression trees had just been proposed, so that was part of the course because I wanted to learn about that. And I remember thinking, you know, when I took a graduate course in multivariate data analysis, I thought this stuff called multidimensional scaling was pretty cool. So I want to teach more about that. And I was teaching that material out of a little monograph by Joe Kruskal and Myron Wish. It's very popular in the social sciences. And it emphasizes an approach to multidimensional scaling that is called non-metric multidimensional scaling. And in particular, it formulates non-metric multidimensional scaling as a certain optimization problem with a criterion that's widely known as the stress criterion. And this monograph, it's very good for applications, but it didn't have much math. It didn't have a lot of theory in it. And I sat there staring at this rather complicated formula for the stress criterion, wondering how I was going to explain it to my students. And I began to sort of break it down piece by piece. And I got to the point where I had a really good understanding where the numerator in this ratio came from. But I was at a loss to understand why there was a denominator in this. And maybe if this had been happening now when I could just Google stuff, I would have done what I could have done then if I'd gone to the library, is just look up Joe Kruskal's 1964 paper, and I would have discovered that there's a sentence that says that the denominator term is there in order to make things scale invariant. And I would have said, oh, okay, that makes sense. And I would have just told my students that, and I never would have done research in this area. Instead, I sat there saying, well, this is an optimization problem, and I know a lot about optimization, and what are the implications of throwing in this denominator term? And I realized that if you didn't have the denominator term, then you just tried to work with the numerator term, you would necessarily, of mathematical necessity, get degenerate solutions where all of the points would be placed at the same location. And I realized that one could think of the denominator as imposing, by means of a penalty function, a constraint that kept that from happening. And I thought, oh, well, that's interesting. And if that's what you're trying to do, then there would be other ways of achieving that end. And I went on to conceive other approaches to non-metric multidimensional scaling. I wrote papers about all of them, and that's sort of how I got into the area. And years later, I actually met Joe Kruskal, who was long since retired, and I gave a talk about some of that. And Kruskal grabbed me and wanted to have lunch with me. And he said, well, this is very interesting. And he asked me all these questions. And I said, I have always wanted to know, when you wrote your 64 paper, did you understand? Yeah, I mean, all you mentioned was the scale invariance. Did you understand that this was a way of precluding degenerate solutions? And he said, absolutely not. He said he had just done that reflexively because, well, of course we want everything to be scale invariant. And he said, I'm absolutely fascinated to see there's another way to approach this problem. So I sometimes think that most of my research is my just trying to understand stuff. I don't really think about, oh, I have to go do something new. I just, people write papers that seem so complicated, and I just think, well, I want to understand this just for me. Fortunately, I have a very high threshold of understanding, so by the time I'm happy thinking that I understand something, usually I have something I can publish. But that's sort of how I got into this topic on manifold learning. Multidimensional scaling is about constructing low-dimensional Euclidean representations of data, and so is manifold learning. And some manifold learning techniques make explicit use of multidimensional scaling. So when this stuff became popular in, sort of 2000 and the years that followed, a lot of people who knew me started asking me, well, what did I think about this stuff? So I was sort of obliged to begin reading the literature and trying to think it through. And I'm still trying to think some of it through, but I think I also have some things to say. So this is partly a talk about things that I think you should know about manifold learning. I do think I know some stuff. But I also think this is a talk about identifying research issues. I'm working on various research problems right now in this area. Li-Zhang Guo is working with me on some of them. I'll mention some of his work later in this talk. So the first thing I want to do is discuss the relationship between manifold learning, which is something that is mainly discussed in the machine learning literature, and dimension reduction, which historically has been something discussed in the statistics literature. And my thinking about this has changed a bit over the years. I used to say manifold learning is just sort of a subset of dimension reduction that's informed by a certain perspective. And now I actually don't think that's correct. I want to argue that they're different. So we'll see if you're persuaded by what I have to say. So let's start. Suppose I sort of tend to mix statistics terminology and machine learning terminology. Let's suppose that we have multivariate observations or feature vectors that lie in some high-dimensional Euclidean space. So that's the RQ, the y sub 1 through the y sub n are the original feature vectors. And by dimension reduction, we mean we want to represent those feature vectors as points in some lower dimensional space. And we might want to do it just for the sake of having a more manageable representation. We might want to do it because it's going to facilitate visualization. We might want to do it as a regularization that improves some form of inference on the data. There's lots of reasons, and I don't want to, it's not really germane to this talk to worry too much about why we're going to do it, but that is what we want to do. And pretty much anyone who has studied much statistics is familiar with some classical approaches to linear dimension reduction. So principal component analysis has been around for, depending on how you count, let's say roughly a century. Principal component analysis can be described in various ways, but basically you can think of it as finding the best affine linear approximation to a data set of some specified dimension. So you say, I start out with data in 150 dimensions, and maybe I can get it down to 5 dimensions, and maybe I can't, but at any rate I can calculate what is the best 5-dimensional approximation. And that's what principal component analysis allows you to do. Now, sometimes we have data, and I'll show you little made-up examples in a moment, that is of lower dimension, but it's not flat. Linear approximations don't necessarily squeeze out all of the structure of the data. And so maybe since about the 80s, I would say, people have been trying to develop techniques for nonlinear dimension reduction. And the idea is that even if you can get it down to 5 dimensions linearly, maybe it's some curved surface inside those 5 dimensions. And if you could flatten it out, you could get it down to 4, even 3 dimensions. So that's what nonlinear dimension reduction is. And manifold learning is sort of an approach to nonlinear dimension reduction. And in other ways, maybe it's something that's a little different. And that's one of the key issues I want to address today, is do we think that manifold learning is just a collection of techniques for doing nonlinear dimension reduction, or does it actually have slightly different concerns? So I've been using this phrase manifold learning. I feel obliged to say a little bit about what manifolds are. I don't want this to be too technical, but I've put a couple of definitions up. Basically, manifolds are surfaces that locally look like Euclidean space. So if you take a small enough piece of them, they can be flattened out and they just look like familiar Euclidean space, and you can do the same kinds of things you do in Euclidean space. And there's various restrictions. We want to assume that everything maps smoothly, and we want to assume that the dimension of the Euclidean space doesn't change as you move around the manifold. But basically, manifolds are surfaces. Riemannian manifolds, yes. Not for the purpose of this talk. I mean, then we're talking about objects that are not manifolds. So this is what we mean in mathematics by a manifold. Now, one could ask the question, what are we going to do with data which in one region look like they're 3-dimensional and in another region look like they're 5-dimensional? And the best answer I have for you is try to identify those regions and do different things in those regions. But I'm not going to try to address that as a principled problem. Yeah? Riemannian manifolds are what you should think of as metric spaces. So the idea of a Riemannian manifold is that you can impose structure on the manifold, and it's done by looking at individual points and the tangent spaces at individual points, and assuming that you have inner product structure in those tangent spaces that varies smoothly. And using that inner product structure, you can define analogs of straight lines, and you can define analogs of distance, and you can show that the minimum distance along the manifold between 2 points follows the manifold definition of a straight line. So it's a natural generalization of the metric properties of Euclidean space. And that actually is going to be important for this talk, is to have metrics on things. So manifold learning is a collection of techniques that are concerned with identifying manifold structure, and they're motivated by mathematical properties of manifolds. And as a result, they, in some way or another, are going to proceed by trying to localize the data regions. So the idea is we want to treat things, we want to have Euclidean representations of things. Manifolds look locally like Euclidean space. So we've got to somehow localize things and say, well, this is a region that's small enough that I can treat it like I would treat Euclidean space. And there is an obvious trade-off here. The smaller you make the neighborhood, the more Euclidean-like it's going to be, but the less data you'll have in it to use to actually do something with. So virtually every manifold learning technique, whether explicitly or implicitly, is going to have some kind of localization parameter that tells you how big or how small those neighborhoods need to be. And here there's a cultural difference, because computer scientists and mathematicians look at this localization parameter and they say, oh, it's a feature. You know, let the user decide what to do with it. Statisticians worry a lot about how do you choose these things, and with good reason, because the effects on the representation of the data can be enormous depending on how you choose these parameters. So here's my little example of a manifold that I'm going to use for several things in this talk. So it's just a spiral that begins here and winds its way out and ends here. And the idea is if you just take a little local patch of this, it's basically looks like a straight line, so it looks like one-dimensional Euclidean space, and it's easy to flatten out one of those local patches. Okay, now I want to think carefully about what is really the goal of manifold learning and what is really the goal of dimension reduction. So this quotation is the first paragraph of one of the two seminal papers on manifold learning. It's the paper that proposed a technique called locally linear embedding. And various other authors kind of say the same thing. They argue that really high dimensional data can't possibly have as many dimensions as there are measurements. And a classic example is images. So you're looking at pixel intensities, maybe 3 intensities if you're doing things in color, at maybe hundreds of thousands of pixels. And yet we don't really believe that you need that many degrees of freedom to parametrize, say, the space of human faces. Now, here's where things are very interesting. They say leads to strong correlations between inputs generating observations that lie on or close to a smooth low-dimensional manifold. And I want to argue that this distinction between lie on and close to is absolutely critical. Because in statistics, as a statistician, I don't know of too many data sets where the high-dimensional data lie on a low-dimensional manifold. Maybe PCA can recover 98% of the variation in 5 principal components, but we don't think that the data really lies on that 5-dimensional manifold. And yet a lot of the thinking in manifold learning has been to assume that the data literally lies on the manifold, and some of the techniques that have been proposed are very sensitive to that assumption. So that's the first distinction I want to draw. The second is, what are we really interested in here? Are we interested in representing the manifold, or are we interested in representing the data? I will be discussing at length a technique called Isomap, which is usually regarded as a fairly limited sort of manifold learning technique. And I'll argue it's because Isomap is largely misunderstood or misapplied. And the thing I want to point out for future reference is there's a mathematical theorem that says if we have a compact Riemannian manifold, we can embed it isometrically in a Euclidean space of some dimension. Now, isometrically means all of the geodesic distances on the manifold are preserved in that Euclidean space. So if the goal is simply to have a Euclidean representation of the data, we might not be interested in dimension reduction. We might be interested in going to a higher dimension in order to get a more faithful Euclidean representation. There can be a tension between those two objectives, and I think it's important to think about that when you think about these techniques. Now, back to my picture. this is an interesting picture. I've superimposed some data on my picture of the one-dimensional manifold. And you can think about this picture in, I think, at least 4 different ways. So first, I could have done this for you, but just try to block out the spiral. Suppose you just had the blue dots there. What would you do with the data? Well, you could say, I have a 2-dimensional data set, and I'm happy. That's all I want to know. You could say, well, I have a 2-dimensional data set, and I could have a more effective 2-dimensional representation if I took this sort of envelope that winds around like this and contains all the data, and I could sort of unroll that and flatten it out, and then instead of having to follow the data around in this pattern, it would just be sort of linearized, and maybe I'd be happy with that. Or I could say, well, I've got this 2-dimensional data set, but it's pretty tightly clustered in this certain intriguing way, and I could actually fit a curve to that, which is this black curve, and that's a nice 1-dimensional summary of the data, especially if I then unravel it and flatten it out. Now, that's almost like manifold learning. In manifold learning, what we're saying is there actually is this manifold, and we've observed data that possibly through measurement error lies close to it. And that's actually how I generated this. I actually did generate the spiral first, and then I just randomly sampled some stuff around it. But those different perspectives conceivably lead you to do different things. So these are some of the classic early references in manifold learning. I put them up for 2 reasons. One is I wanted to give you a sense that these are all techniques that are very consciously trying to exploit the notion of what a manifold is. So, you know, this Isomap is trying to capture geodesic manifold distances. Locally linear embedding is geometric in some way that's maybe a little unusual. I mean, Laplacian eigenmaps, he talks about things like the Laplace-Beltrami operator on manifolds and so forth. And it was sort of my initial feeling like, well, what really unites this literature is just that they're using the idea of a manifold kind of as a metaphor to give them ideas about how to do nonlinear dimension reduction. I think that there's a little more to it than that now. But let me point out why it might take a while to get to the perspective I'm trying to articulate. Look at the sentences here. I've highlighted. Every one of these talks about the technique as doing dimension reduction. At least the title says that manifold learning is just an approach to dimension reduction. But it's not so clear when you follow the research that that's really what people are thinking. So the manifold learning perspective, if you start digging into the literature, they really do enforce this assumption that the data lie on the manifolds. And they use phrases like the true structure. It's not something that they've invented because it fits the data. It's really where the data is coming from. And they prove theorems about under certain sampling schemes, when will a certain technique be able to recover this true structure. And from that perspective, Isomap has been criticized for not performing under as broad a set of conditions as some of the other techniques do, and I'll elaborate on that later. I think that the dimension reduction perspective is a little different. Regardless of whether you believe that the manifold is the true structure, certainly we can say that if there is a meaningful low-dimensional representation of the data, it is in some sense saying that the data lie close to a manifold, and our goal is to find it. But that doesn't necessarily mean that we think that there's a true structure, and we certainly are not likely to want to live with assumptions that require the data to lie on the manifold. So, like I said, I think this distinction between lie on and close to is very important. So now let's start talking about specific techniques. Yeah?
So is one way to say the distinction between true structure and then a line close to is that in different regions the approximation of true structures is going to have the same errors, and in case of line close to in different regions the approximation might have different errors? Is that true?
Well, I think it's more fundamental than that. I think there's a basic question about what models are realistic for what applications. So if I don't remember, Shantanu, were you at the talk that Carrie and I gave last month? So you'll recall we had a situation there. We weren't trying to estimate a data manifold. It was actually a statistical manifold of distributions, but we had estimates of points, and those were statistical estimates. There's no way that they could be guaranteed to lie on the manifold. Some error was inherent in the process, and we'd like, at the end of the day, to have results that say that if we collect more and more of those estimates, we can recover the actual statistical manifold. There is an actual statistical manifold, but there's no results in the manifold learning literature that say that provide those kinds of results, except for situations where the data lie on the manifold. Okay, so let me tell you a little bit about Isomap, which is probably the most popular of the manifold learning techniques. It is the easiest to understand, which is probably why it's the most popular. I think it's been given kind of a bad reputation, probably, again, because it's so simple to understand. But let me sketch it for you and make a few comments. So the first part of this, of Isomap, is the localization part. What we do is we try to connect points, feature vectors, that we think of are close together, thereby creating a graph where there are edges for things that are local, and when things are not local, there are no connections. And then, and I'll show you a picture in a moment, then in the second step, we use the graph to try to approximate the shortest distances on the manifold, the geodesic distances. So the idea is use shortest path distance on this. The graph's supposed to approximate the manifold. Use shortest path distance on the graph to approximate geodesic distance on the manifold. And then you just want a Euclidean representation. So the third step is just the traditional step where you've now got a matrix of dissimilarities, the shortest path distances on the graph. They use classical multidimensional scaling to embed. Since the goal of this is to approximate the shortest path distances with Euclidean distances, you could make a point that it makes more sense to do some stress-based approach. They said they wanted to do classical because they thought it was less computationally expensive. It's actually more computationally expensive if you do things in the right ways. But really, I mean, here's my message to the students. The real mistake was in defining Isomap is to say, in step 3, embed by classical multidimensional scaling. That was not novel. They had two very clever ideas here, and then they just did something traditional here. They shouldn't have said Isomap is when in step 3 you embed by classical multidimensional scaling. They should have said step 3, embed using your favorite multidimensional scaling technique, and staked out more territory for their method. But in any case, that's not what I want to talk about. Let me show you what Isomap is, and then I'll come back to the bottom of this. So here's the picture again, the data points, except now that I've connected nearby points. And the rule that I used here was I drew in an edge whenever 2 points were within half a unit of each other. Now, obviously, things can change depending on how you choose that, or whether you do it based on nearest neighbors. And in fact, I'm right on the borderline here. When I did this randomly several times, sometimes the graph would end up being connected and sometimes it would not. But this one is connected, so I'll use it. And the point is, here's 2 points connected by this red line, and they're pretty close together in the ambient Euclidean space. But they're not at all close together if you think of them as being on or close to this manifold, which goes all the way around like this. And so if you construct this graph and then do the shortest path distance, which I haven't tried to calculate or displayed, but basically you're going to zigzag all the way around here, and you're kind of going to follow the manifold distance. That's the idea behind Isomap. It's a very clever idea. And then when you do the embedding here, this is what you get. So this is the classical embedding of those shortest path distances. And you see that things are pretty much flattened out. These are the first 2 principal components. Clearly, the second one isn't adding very much. If you just treated this as being in 1 dimension, you'd basically have flattened out that spiral structure. And just to show you that the points are in the right order, here's the 2 points that I'd connected, and you see they're pretty far apart now as opposed to being pretty close together. But here's the interesting thing. I think the idea behind Isomap is really interesting. I think it's a very nice idea. But the key is you're going to try to represent geodesic distances on a manifold with Euclidean distances. And we know, if you just think about the mathematics, the Nash embedding theorem says to really do that faithfully, you may need more dimensions. Now, in this case, you didn't need more dimensions. I mean, 1 dimension works just fine here. But there is a belief that if you've got a 5-dimensional manifold, then what you should do with Isomap is construct a 5-dimensional representation. Well, if the goal is to have a 5-dimensional representation, maybe so. If the goal is to have a good Euclidean representation of the structure of the data, you might want to consider more than 5 dimensions, because that is what that technique is trying to do. And I'll show you an example later where I think people have misinterpreted it. And by the way, I think this is not something that people take too readily. I mean, those of you who met or saw Kerry Priebe when he was here, I mean, Kerry and I have been working together for 20 years. We talk about this stuff all the time. When I tried to convince him that you might want to do Isomap in a higher dimension than the dimension of the manifold, I mean, that just blew his mind. Yes?
I think that's a wonderful idea. But isn't there always this concern of overfitting?
Oh, well, certainly if we have what Kerry would call an exploitation task. So after we embed the data, we are going to do something like construct a classifier. Then you can ask that question in a meaningful way, and you can say, well, in what dimension am I going to achieve optimal classifier performance? You can think of the dimension as a regularization, and it's no longer a question of what is most faithful to the data, and indeed, we know that sometimes you don't want the most faithful representation, that you can filter out some noise and do a bit more powerful inference by getting a cruder approximation. That's not really what I'm talking about here. I don't have an exploitation task in mind. So if I was talking about that, I'd agree with you 100%. But if we're just talking about trying to capture the structure of the data, then I don't think there's such a thing as overfitting. I mean, the more we can capture, the better. You may have competing objectives. You might say, I want to fit as best I can, but I also want to not use any more than the following amount of storage space. But I think that until you introduce some inferential task that you're going to do subsequently, there really isn't a notion of overfitting. That's my take on that. Okay, so now I want to just very briefly mention Laplacian eigenmaps. Laplacian eigenmaps are in many ways very similar. Yes?
Sorry, before you go on to the next slide, can you just explain what classical multidimensional scaling is doing when you say, oh, embed in the classical way? I'm not really sure what that is.
Well, this is wonderful because usually I explain this in the exact opposite way, but since your training is so modern, I can say classical multidimensional scaling is kernel PCA. And that actually makes sense to you, right? Yeah. So the only difference is that in kernel PCA, we tend to start out with an inner product matrix, and then we factor it to get the Euclidean representation. In classical multidimensional scaling, we start out with dissimilarity measurements, and we think of them as Euclidean distances. We convert them to squared distances. There's a linear transformation from squared distances to inner products. And then at that point, it just becomes kernel PCA. So, I mean, it's interesting. Machine learning people, I mean, I've seen people talk about they always say multidimensional scaling. Classical MDS is the only kind of multidimensional scaling they know. And they talk about it as kernelized multidimensional scaling. Well, no, it was kernelized when it was invented back in circa 1950. That was the point. It's actually, I mean, the oldest kernel method I know. Okay, so actually I'm not sure I think I will skip the Laplacian eigenmap stuff. I don't have very much that I want to say about it, and I think we're running a little short on time. I'll say a little bit more about locally linear embedding, which together with Isomap was one of the original two manifold learning techniques. And the idea, which seems appealing, and then the more I think about it, the more I think I don't really know why that should work. But the idea is locally look at your high dimensional data, and within local regions try to represent each point as a linear combination of its neighbors. And then say, well, when we try to construct a low dimensional representation, just try to preserve that weighting scheme. Pack the points into a low dimensional space in such a way that, again, each point is the same linear combination of its neighbors. And you think, oh, okay, that sounds pretty cool. And what's on this slide is just sort of the mathematics for how you do that. And I wanted to do this if only to show you this picture. So every paper on manifold learning shows you that they can learn the so-called Swiss roll, which is basically my spiral extended to give it another dimension. So you can see it's sort of rolled around like this, and the goal is to, these are screen grabs off of the papers, which is why they're kind of fuzzy, but I think you can still see what you need to learn. So what they did is they took data, this is points on that manifold, and it's color-coded so you can sort of watch it unroll. And they did this technique, and indeed, they flattened it out. Now it looks like just a piece of paper that has been unrolled here. So this is an example of manifold learning works. It unrolls the Swiss roll. And then, of course, the next thing they do is apply it to some incredibly complicated data set and claim that they've learned something. Well, so that's an example of it working. Now, the next example may give you pause for thought. So this is a really, really simple data set that I constructed. There are 7 feature vectors. They're points in R3, but by design, they have a very highly linear structure. So basically, the first component is all the information, 1, 2, 3, 4, 5, 6, 7. And then there are just tiny little perturbations. So epsilon here is symbolic. You can make it as small as you want. The analysis does not change. And now there are several slides that go through the math, which we don't need to do. But here's the LLE representation of those 7 points. Now, basically, there are 7 points spread out on a line. And this is supposed to be a manifold learning technique that detects linear structure. And the solution is to put the 1st and 7th point at this location, the 2nd and 6th point at this location, the 3rd and 5th point here, and the 4th point here. Now, I don't have a very good explanation right now of what goes wrong there, but something surely goes wrong. And so for me, I'm a little nervous. I think you should be a little nervous about using a technique like LLE on a very large and complicated data set and being convinced that you have learned some structure. I mean, if it can do this to this data set, Lord only knows what it can do to some complicated data set. Okay, the last thing I want to talk about, because Li Zhang and I have been doing a lot of work on Hessian eigenmaps. This is Hessian eigenmaps are similar to locally linear embedding in the sense that they explicitly try to construct local patches and proceed from that. They argue, the LLE people, the Hessian eigenmap people, argue that they're doing something fundamentally different from Isomap in that Isomap explicitly tries to construct global information by looking at these shortest path distances on the graph. And they're only looking at things in local neighborhoods. And so somehow they have more flexibility. It's like they're constructing the representation only from local information. And I think this is kind of silly because they are constructing a global representation. I mean, they end up with a set, the entire set of data points in the same picture. Now, the local information may not be enough to determine, typically will not be enough to determine the unique global representation. Think about molecular conformation. You know the bonds between different atoms. Maybe you know the bond angles. You build a little model of it. There's still usually a lot of slack to move it around and get different three-dimensional conformations. Same thing is true here. So when a method uses only local information to construct a global representation, it's got to be imposing some kind of structure someplace. And it may not be easy to find what it is. At least in Isomap, it's pretty obvious what it's doing. It's not as obvious what LLE is doing. It's not as obvious what Hessian eigenmaps are doing. Now, the great virtue of this paper on Hessian eigenmaps by David Donahoe, the Stanford statistician who some of you heard speak last year, and his student, I forget her first name, Grimes. The great virtue is that they define a very specific manifold learning problem. Most of these techniques, they don't really tell you what problem they're trying to solve. I mean, they sort of say, well, we're trying to find the manifold that the data lives on, and sometimes people have proved techniques about convergence and so forth. But they're really good about saying, here's the problem. They call it the parametrization recovery problem. And they say, well, suppose that we've got a manifold that's been parametrized. So let's say theta are the parameters, and they're an open subset in RD. And you've got a function psi, so that psi of theta gives you some manifold in some Euclidean space. And they say, well, the problem is to try to recover the parametrization from the manifold. And they assume that the manifold is locally isometric to some open connected set so that this is possible. And then they propose a technique that actually allows you to recover the parametrization. And here's, mathematically, here's the solution. Imagine that you have various functions, that real-valued functions on the manifold. You define what they call the Hessian functional on these functions. Basically, what you're doing is you're just integrating the squared norm of the Hessian matrix as you move around on the manifold. And you can show that it does not depend on the parametrization that you, or the coordinatization you use to write down the Hessian matrix. And you can see that unless you have an affine function that someplace on the manifold the function is going to have a Hessian whose norm is positive, and so this will have a positive value. The only way for this functional to be 0 is if f is affine, in which case the Hessian term always vanishes. And so then they show that you can extract the coordinates from the null space of this operator. And the technique of Hessian eigenmaps is to try to come up with a discrete approximation to this continuous operator, and then to try to get the null space of that discrete approximation. This is very fragile. You are, in essence, trying to do second-order differencing to estimate quadratics, and it can get messed up very easily. But that's not really the part of the problem I want to talk about today. What I want to talk about is the logic behind this problem, and is this the right problem for thinking about manifold learning? So here's another screenshot that you can barely see. This is the basic Swiss roll again with data on it, except, and you can't see it very well in the data because it's rolled up, but right around here, they've cut a square out of it. And here's their solution, which is exactly what they wanted. They've unrolled the Swiss roll with a hole in it, and now you see, well, here's the rectangle that they cut out. So this is like, what the picture they look at and say, this is what is supposed to happen, and we do it. And here's LLE, which you do see a hole in it, but it's sort of got this weird structure, and it's hard to understand where that structure came out for the reasons that I showed you. And here's what Isomap does. And what they say, let me see, do I actually have the quote? They say, in the case of Isomap, the non-convexity causes a strong dilation of the missing region, warping the rest of the embedding. Hessian LLE, on the other hand, embeds the result almost perfectly into two-dimensional space. Well, I think this is a little unfair to Isomap. Yes, it is true if the problem is the parametrization recovery problem, then yes, they've solved it. Isomap really has not solved it, and the point of their paper is that Isomap can only solve the parametrization recovery problem under more stringent conditions. It needs a convex theta, and there has to be global isometry, not just local isometry. But I would argue that this was never what Isomap was designed to do. Here we have a Riemannian manifold, and there are geodesic distances on it which have a certain structure because they have to go around that hole. And now the question, what Isomap tries to do is represent that Riemannian manifold in Euclidean space. And by the Nash embedding theorem, it could probably get it, the Euclidean distances to match almost exactly if you went to a higher dimensional space. If you want a two-dimensional representation, what this is this is the best two-dimensional representation of the Riemannian structure of this manifold, which is a different problem than the parametrization recovery problem. So that's basically what I say here. Now, Li Zhang and I struggled all summer just to understand this Hessian Eigenmap paper. It's very badly written in the sense that they just sort of sketch ideas and don't explain how they're going to solve them, and then they don't actually do the things they say they're going to do, and it took us forever to sort of figure this out. But I think we finally really began to understand what it does, and then we wanted to understand, well, when does this work and when does it not work? And I think that it eventually dawned on me that the paper, while it elucidates the technique, it doesn't really give much insight into when the technique works. They prove a theorem that says it can recover the parameters when the parameter space is locally isometric to the manifold. Well, locally isometric says it's possible to do this. So in essence, the result says the technique works when it works. Well, when does it work? So this is where Li Zhang did some really interesting numerical experiments. So he started messing around with two-dimensional surfaces in R3, something we can actually kind of visualize. And we looked at Swiss rolls, and after a lot of sort of false starts, we finally got to the point where, yeah, we could reliably learn Swiss rolls with this technique. And then he looked at other surfaces. I don't think he actually looked at a hemisphere, but he looked at things that were sort of hemisphere-like, that he'd sort of like, were more hills that were rounded in different directions. And it turned out in his experiments, while it worked fine on Swiss rolls, it didn't work so well on things like hemispheres. We were trying to understand why. Now, Li Zhang conjectured, and I don't know how he came up with this conjecture, maybe just empirically what seemed to be working, but he conjectured that the difference between when it worked and when it didn't, the difference between Swiss rolls and hemispheres, is that it only works well on surfaces with zero Gaussian curvature. So Gaussian curvature is if you look at a two-dimensional surface, you basically look at arcs through the point and how much they're curved in different directions. And you can show that the directions of maximal curvature and minimal curvature are orthogonal to each other, and those are the two principal curvatures. The product of those two principal curvatures is the Gaussian curvature. So Gaussian curvature 0 means it's flat in one dimension, or possibly both. So Euclidean space has 0 Gaussian curvature. The Swiss roll has 0 Gaussian curvature because it's curved in one way, but it's flat the other way. And the hemisphere does not have 0 Gaussian curvature. In fact, it has constant positive curvature. So that was the conjecture. And now this is the really pretty punchline to this part of the talk. Never before, and maybe never again, am I going to be able to use a famous theorem of Gauss in a statistics talk. But it turns out that there's two theorems that directly address this. So remember, what we're trying to do is say, well, when is something locally isometric to Euclidean space? And this theorem, I didn't know about this until quite recently. Minding's theorem says that all surfaces with constant Gaussian curvature are locally isometric. So all things with constant zero Gaussian curvature are isometric. So anything that does have zero Gaussian curvature is locally isometric to two-dimensional Euclidean space, and therefore Hessian eigenmaps should work in that situation. The converse is more interesting. So this is the famous theorema egregium, or remarkable theorem of Gauss's that he was so excited about. In many ways forms the basis for later investigations in Riemannian geometry. So Gauss's theorem says that Gaussian curvature is invariant under local isometry. So what that means is if you start out with something like the hemisphere that does not have zero Gaussian curvature, and you do anything that's locally isometric to it, it can't have zero Gaussian curvature either, which means that you can never make it locally isometric to R2. So what this result therefore says, a corollary of it, is Hessian eigenmaps can't work if you don't have zero Gaussian curvature. And so this for me is wonderful. It answers this question: why does every single paper on manifold learning begin with the Swiss roll? Well, in some sense, this is saying the Swiss roll is the only example in which the stuff can actually work, which I think is just a remarkable result. Now, like as I've argued, I do not think the parametrization recovery problem is the manifold learning problem. It was a problem for which Donahoe and Grimes found an elegant solution, but I don't think it's the problem that we usually care about. And I don't think it's fair to criticize Isomap for not performing well on the parametrization recovery problem. It's designed to do something else, and it does it quite well. So I think I've exhausted my time. I will leave you with that thought. These slides are already up on my webpage, should anybody be interested in them. It may take you a little effort to find them. Go to my materials for courses, and go to my 675 course, which is on statistical learning and high-dimensional data analysis, and read down in the syllabus. And at some point, there is a link to this talk. It's in the little section on manifold learning, obviously. And, you know, I love this stuff. I mean, this is, you know, one of the things I spend a lot of my time thinking about. So anybody who wants to talk about this with me, please get in touch. I'd love to have those conversations. Thanks for your attention.
So we probably have a minute or two or three questions maybe.
Rob.
So I have a really basic question maybe. Take it maybe for Isomap as a good case for it. So I understand how Isomap unrolls the Swiss roll, but I don't understand the sense in which it is recovering the true manifold as a Swiss roll. Is it
Well,
somehow magically getting these global properties?
I mean, I think that this is where one can quibble about what does true structure mean. I mean, if the true structure is a torus, is the solution to say it's a torus, or is the solution to find a useful representation of the torus? And I think that sometimes those are different. I would argue that what Isomap is trying to do is provide a Euclidean representation of the Riemannian structure of the manifold. So if what you care about the manifold is the metric information, if what you care about is how to represent feature vectors in a way so that similar feature vectors are close in Euclidean space and dissimilar ones are far apart, and you want to do that metrically so that the Euclidean distances in the representation approximate as best as possible the geodesic distances on the manifold, then that is literally what Isomap does. And where can things go wrong? Well, in the first step where you're trying to localize, you could just end up with insufficient data that you could effectively localize, or you might choose the wrong localization parameter, and you might fail to do an adequate job of capturing the manifold structure. The shortest path distance is the computational bottleneck, but conceptually, I think it's as good as the data is. If you've got a lot of data and they're pretty close to the manifold, and I mean, usually they talk about it being on the manifold, but the example I showed you, it was just close to and that's one thing I like about Isomap. The logic works whether the data is on the manifold or close to it. Then those shortest path distances really should do a pretty good job of approximating the geodesic distances. Again, it can only do as good a job as the data you have and the localization that you choose. But the shortest path distances really are literally trying to approximate the geodesic distances. And then the embedding step is just how good a job can you do of matching the shortest path distances with Euclidean distances. So you've got your choice of various multidimensional scaling techniques. I would argue that there are a number of reasons to prefer the metric stress criterion, which is literally trying to fit the Euclidean distances to the shortest path distances. There are games you can play to make it computationally feasible for large problems, and you can also play games with weighting different pairs. So you might do stress embedding where you weight the local distances more heavily than the distant distances to get something you're happier with. But I think really the key issue is this neglected issue of how do you choose the embedding dimension. And I think that if you adopt the perspective that Isomap is intended to give you a Euclidean representation of Riemannian structure, geodesic structure, then you think about that problem of how to choose the dimension very differently than if you just start out saying, well, how many dimensions do I need to describe the data? Chris.
Well, just thanks for a wonderful talk. My favorite talk is where I learned something. Will you go back to one of your very first slides where you showed the snail or the spiral?
With the data?
Red line that connected these two points that were not close to one another on the right there.
Yeah. Now, well, do you want? Here's the one with the data. Do you want this one or you want the one with the graph?
The one that you just went by.
Okay. Okay.
So the fundamental assumption, it seems to me, of Isomap is that when you construct your graph, this red line never appears. That you connect two points
Correct.
that are not adjacent.
Correct.
So my question, isn't that sort of a brittle assumption? I mean, if you have just one of those, all of your distances are nonsense.
Well,
so how can this work with such a seemingly brittle assumption?
Well, certainly any of these techniques are going to work better if the data is close enough to the manifold to mitigate that problem. So to some extent, you're just pointing out how convenient it is to assume that the data lie on the manifold, and then we avoid this issue. I think I would also say you're making a point that I tried to make, which is that these techniques are very sensitive to the choice of the localization parameter. And you're absolutely right. If you imagine maybe a slightly less restricted cloud of data points around here, you could see, how I choose the epsilon is going to decide whether there's anything that connects these two. And in this case, I'd have to get, you know, a lot larger than I was to begin connecting these. But you can see, I mean, once epsilon gets up to be about this big, I'm going to lose this ability to follow the manifold. So you're absolutely right. One thing that you know, I basically didn't talk about the Laplacian eigenmaps, and if I had, I would have given you a perspective on Laplacian eigenmaps, which is a little different than the usual perspective, which is that you're doing exactly this, except once you have this graph, you're not computing shortest path distance, but you construct a random walk on this graph and compute expected commute times. And the hope is that that will mitigate the problem you've identified, at least to some extent, because you might have one way of getting there, but there's lots of ways of getting around this way. And so when you weight those probabilistically, it may mitigate the problem a little bit. It turns out to cause lots of other problems, but you know, it should do a little better with the problem you've identified. But yeah, it's a very legitimate problem. And it basically just says, if you really do have a nonlinear structure that you want to learn and the data is noisy, which it usually is, it may be really difficult. And there's actually some simulation experiments I found on the web where they were just trying to compare manifold learning, various manifold learning techniques, and they just kind of threw in PCA, I think, to sort of show how badly it performed, except it actually outperformed most of them. And you know, if you think about it, right here, you know, PCA is going to say this is clearly two-dimensional data, and we know we can get it down to 1 if we do the right thing, and that looks like a big difference. But I wonder, with real data, you start off in 500,000 dimensions, you're going to compress it down to 1,000 dimensions, say. What do you really gain by using some nonlinear method that, you know, sort of picks up some of this curvature? I mean, if what you're getting is that you can get the same degree of fit in 996 dimensions where PCA would take 1,000 dimensions, why go to all the trouble? Is that difference in 4 dimensions really worth it? And I don't think there's been much systematic exploration of that issue.